Hello, afternoon, everyone. Let's just wait for another maybe 5 minutes to see if there are more people coming. And before we, excuse me, before we start our lecture today, do you guys have any questions regarding the project or the homework?
Yeah, sorry. So I was looking at lab 2. When is the exact due date?
Let me check. It should be 3 weeks after the lecture.
Okay, thank you.
Can you guys see my screen?
Yes.
Okay, great. Let's give it another 3 minutes. So how do you guys think about the homework and the lab session? Do you think it's too easy, too difficult, or do you have any thought about it?
Personally, it seems fine to me. Nothing too crazy.
Yep.
Just yet.
I agree.
Mm-hmm.
Yeah, same.
So do you guys have any any thought about that? Like, would you think we could improve it, or
Is it 63 degrees where you are?
sorry?
Is it 63 degrees Celsius where you are?
Let me
It
check.
says it on the top of your screen.
No, that's the temperature of my computer.
Oh wow, that's hot.
Yeah. Wait, which screen are you looking at? Because it's supposed to be showing this. It's supposed to show this slideshow.
Yeah, we can see the slideshow. It's just that above it shows that.
Oh, okay. Yeah, that's fine. All right. So let's start our lecture for today. Oh, sorry. Okay, it should be back on. So today, let's talk
Bowen,
about.
when is lab 2 due?
I'm sorry, I can't remember when we had lab 2. That should be 2 weeks ago, right?
Yeah, I think it is.
That was a week
ago. Yeah. Then you still have one more week to complete that.
So we have one more week.
Yeah. So for each lab and homework, you will have 3 weeks to complete that task. Let me admit the students in.
Okay, now I see it.
Okay, let's start. So today we're going to talk about the final project, omniaxial, the elbow exoskeleton. We actually talked about this a little bit last week and between the lectures. So let's look at the outline of our today's lecture. The first part will be the project overview. So it's going to be a printed wearable robot, and each of you will be a group. Because of the condition right now, you will be doing this project totally on your own, off campus, and we will provide you a lot of things, but the most importantly, you can't come down to the campus. We can only provide you remote help. So good luck with that. Oh, sorry. So you need to design and assemble. Yes, sorry. Hello, I'm sorry. Can you please mute? Thank you. So for this project, you need to design and assemble elbow exoskeleton using 3D printed hardware, servo motor, and a torque sensor. And of course, AMU, then we will talk about that. The exoskeleton position, torque admittance control, and virtual wall. Use inertia measurement unit, IMU sensor, and for motion intensity control the elbow exoskeleton. So on the left, here is an example. In the middle, that's the mechanical parts. And on the right side, that's the electric parts. The goal for this project is to design the elbow exoskeleton that is workable with the provided parts. Control part, we will need to realize the position control through the feedback servo motor, the torque control, and admittance control, and a virtual wall. And an optional, I'm sorry, this is not optional, but the human in the loop control, that's the optional part. For this part, you need to use an IMU to feedback the servo motor and the load cell to control this exoskeleton. And most importantly, you need to understand the working principle of robots. The tasks will be design. You need to design the elbow exoskeleton and send us your design for validation. The top 5 designs will be 3D printed and the rest will receive our standard omniaxial kit. But don't worry, if your design was not chosen, your final grade will not have any deduction from it. But those 5 designers who got chosen, they will have extra bonus. And also you need to assemble and function test the exoskeleton, realize the admittance control and virtual wall control, and include the codes and video links in your report. And the optional human in the loop control, and include the code and video links in your report, of course. And a brief background introduction about robots. A robot is a machine, especially one programmed by computer, capable of carrying out a complex series of action automatically. Robots can be guided by an external control device, or the control may be embedded within. Robots may be constructed on the lines of human form, but most robots are machines designed to perform tasks with no regard to their appearance. So there are a lot of many different kinds of robots, and you can categorize them through different ways. You can categorize them in a way like how they look. There will be human-like robot, arm-like robot, and if you categorize them through the function of them, there will be aerospace robot, there will be underwater robots, there will be a lot of them. And for this project, we're talking about the wearable robots. A wearable robot is a mechatronic system that is designed around the shape and function of the human body, with segments and joints corresponding to those of the person it is externally coupled with. So here we show the most famous wearable robot and exoskeleton. But of course, a wearable robot can be as small as a glove or as a suit. It doesn't have to be like as cool as the Iron Man suit. It can be anything you can think of. So in the last decade, we have made significant progress in the information technology, robots, and the information and AI. A lot of them are just booming. So robots are not just the tools. The interaction between human and the robots than just using a tool. Can you please mute? Thank you. Like Elon Musk, the big boss of Tesla, SpaceX, he thought that we are already a cyborg. So he said, and I quote, "To some degree, we are already a cyborg. You think of all the digital tools that you have, your phone, your computer, the applications that you have, the fact that you can ask a question and instantly get an answer from Google and other things. That's a fearing thought, I would say. We're living in a world that with all of these digital ghosts. However, with all those booming information technology, there are still very limited systems that can deliver physical service like a wearable robot. So this is where our project, the meaning of our project, we are giving you an opportunity and giving you a platform so that you can learn what a wearable robot is and learn how it works, and maybe from here you can get a career in this path. And let's show you some videos. Can you see this video? Hello?
We can't see the slides.
Still the slides?
Yeah.
Sorry. Wait a second.
Now we see you.
Now you can see the video, right?
Yeah.
Yeah.
Figure out what you want. Yeah.
All right, collecting.
So this is elbow exoskeleton.
All right, go ahead, do the full bend.
Yeah, I'll make sure I'm all set. Oh, okay.
So this is the hardware of it. And here is another one.
What?
Sorry, can you see this?
Yes.
Yes.
Yeah,
Graduation season, and if you think your kids are smart, they may be so, but nothing like as smart as those that won the Cornell Cup. Welcome to Digits. I'm Simon Constable, and we have one of the team members who won the Cornell Cup this year. It's Nick McGill, University of Pennsylvania graduate, just graduated earlier this week. There he is. Nick, thanks for joining us. Congratulations on winning the Cornell Cup. Why did you win? I think it has something to do with the apparatus you're wearing.
Thanks, Simon. Yeah, so I'm part of the Team Titan from the University of Pennsylvania. My team members, Elizabeth Beatty, Nick Parada, and Nikolai Vladimirov, supported us through the entire project, and we developed a powered upper body exoskeleton. So you can see right here I'm wearing this apparatus that goes along my bone structure. Right here.
And what is it used for, Nick? I mean, it looks very fancy. It's clearly impressed the judges. But for folks who don't really know the technicals of it, how would this be used?
Yeah, so when we envisioned this project, we wanted to do something that would be applicable to those who had upper body injuries. So we developed a project that has a motor at the elbow joint. So right here, it's actually used for physical therapy and healthcare applications. You'll see that we've got a power joint on the elbow, so you could imagine using this to rehabilitate your muscles. And on each of the joints, we have Hall effect sensors. These allow us to track the range of motion of each of the joints.
And how did you come up with the idea for that? Is that something personal? You thought, okay, this is something that's not out there, needs to be?
Yeah, so I actually got really interested in, I guess, healthcare and electronics last year when I took Professor Mongram's course in embedded systems. I worked on a project using the Microsoft Kinect to develop an at-home physical therapy system. Once I got involved in that, I started realizing that there are a lot of great applications, and a lot of my team members had great input on different sorts of healthcare applications, and had some good stories as well.
Now, I understand there's a very large, heavy weight just off camera there. You're going to get that now and demonstrate for us how this might work.
Sure thing. Nico, can I have the weight? So right here, Nico just handed me a 20-pound weight. So basically what it allows me to do, this suit gives me extra strength so that I can, add on to my additional strength. And also, if I put on the ratchet braking, it gives me the ability to hold the weight in place. Now you can imagine in a warehouse setting where you're lifting a lot of heavy boxes or weights, you're going to be walking with a big box and you want to hold it in place. So our suit has the capability to hold this weight, and I don't have much fatigue at all.
So if I wanted to be a muscle man, there is still hope for me. What is the maximum amount that arm can lift?
Yeah, so this arm, we found that we can add 40 pounds onto what your lifting capability is in existence. Now, we weren't trying to max out the weightlifting capability. We were more aiming for assistive lifting and reducing fatigue, as well as our applications in physical therapy.
Now, you and the team have invented this. You got the prize. You got $10,000 between you. What are you going to do with this project now? Are you going to commercialize it and get this sold off and patented and stuff?
Well, hopefully we're looking at continuing development. We're all coming back for grad school at the University of Pennsylvania. We've had all this great support from Cornell Cup and Intel. So with this money, we'd like to continue working on different applications. You'll see right now we've got a joystick for our input. So this allows me to go up and down and control the brake. However, we would love to have electromyography, using your muscles instead to control the exoskeleton. So we're looking right now to work through the summer and next school year into continuing development on this project.
So you're going back to grad school, and congratulations on getting into grad school as well as from graduating.
Thank you.
What will you do after that, do you think? Do you think you're going to become a scientist, a mad scientist if you like, or go and be an entrepreneur?
Well, I'd like to say a little bit of both. I mean, at this point, we've found a lot of great success with the projects we've been working on. So I think we've all been inspired to continue to work on our own projects, maybe develop our own companies.
Okay, thank you very much. Nick McGill, member of the team that just won the Cornell Cup US.
So you've seen these video clips. So if you want to be a mad scientist or maybe some entrepreneur, we just provide you an option. So for our $599, we are not expecting you to do something as fancy as this within such a short period of time, but we would like you to have a big picture of it and where the direction of the exoskeleton, especially for the elbow exoskeleton, the direction of it. So now let's look at some very basics so we can start our design. So first of all, let's talk about the biomechanics, the planes of the body. So there are three major planes in the human body: the coronal plane, also known as the frontal plane, is a vertical plane running from the side to side, dividing the body or any of its part into anterior and posterior portions. The sagittal plane, or sometimes some people may call it lateral plane, a vertical plane running from front to back, dividing the body or anything of its part into right and left side. This is very important plane for our design. You better remember this word, sagittal plane. The axial plane, or sometimes we call it the transverse plane, is an horizontal plane dividing the body or anything of its part into upper and lower parts. And the median plane, this is the sagittal plane through the middle line of the body, dividing the body or any of its part into right and left halves. So this one is a very special sagittal plane, but also it tells us it doesn't have to be in the middle to be the sagittal plane. Anything could be a sagittal plane, like your elbow. The flexion and extension of it, you can consider it is happening on the sagittal plane. Now let's talk about the direction terms. Direction terms describe the positions of structures relative to other structures or locations in the body. The superior or cranial is towards the head and to the body. The upper, for example, the hand is part of the superior extremity. Inferior or caudal, away from the head. Lower, an example is the foot. The foot is part of the inferior extremity. Anterior, that's the front. Posterior or dorsal, that's the back. Sometimes we may call those names. And medial, that's towards the middle line of the body. So for example, the middle toe is located at the medial side of the foot. And lateral, that's away from the middle line of the body. For example, the little toe is located at the lateral side of the foot. Proximal, that's toward or nearest the trunk or the point of origin of a part. For example, the proximal end of the femur joint with the pelvic bone. So can anyone give me another example of the proximal? Because I sometimes find the proximal concept is quite confusing.
So an example is the shoulder. It's like proximal to your torso, and the hand is distal.
Yes. Thank you very much for bringing this new concept to us. The distal, that's away or furthest from the trunk or the point or origin of a part. So hand is located at the distal end of the forearm, and foot is also a distal part located at the distal end of the leg. And now let's talk about the joint motion and positions. So joint motion, there are two very common motions, flexion and extension. A lot of our joint can perform those two motions, flexion and extension. For example, the neck, as the first picture here shows, flexion, extension, and hyperextension. So sometimes, well, this is an easier way for me to remember which one is flexion. Sometimes, let's say if the joint is bent, normally it would be flexion, and if a joint is extended, that would be extension. The second one would be the shoulder joint extension, flexion, hyperextension. The third one, which is the one we're gonna use the most, the elbow joint, use the most for this project, the elbow joint extension and flexion. And also we have the wrist flexion, extension, hyperextension, for the hip joint and for the knee joint. And at our lab, we have a lot of projects going on that focus on the hip joint and the knee joint. Abduction and adduction. Those are for the shoulders, wrist joint, and hip joint. Rotation. So your neck can rotate your shoulder joint and your hip joint. Circumduction. The shoulder joint and the hip joint. From this, we can see that our shoulder joint is pretty flexible, and as well as hip joint. And of course, we have a lot of other motions, special motions, like elevation, depression, that's a draw, protraction, retraction, also the draw, intertarsal joint, we got inversion, eversion, dorsiflexion, plantar flexion, that's for the ankle joint. And we got this opposition, we got pronation, supination. Actually, there's a very interesting way of remembering which one is pronation, which one is supination. So it's like you are holding a soup. So when you are holding the soup, that's the supination. When you pour it, it will be pronation. That's a very interesting way of remembering it. And the joint positions, varus and valgus. This is a normal knee alignment, and this is varus. This is called knock knee, valgus. And sometimes you can have the valgus within your foot that will be called bunion. Let's look at the primary musculoskeletal structures. So for our musculoskeletal system, it enables us to move, to run, to jump, to grasp objects, and so on and so forth. It consists of bones, joints, muscle, tendons, and the cartilages, ligaments, and a few of other tissues like disc, meniscus, labrum, flat fat. The connection between bones is called a joint. The geometry of our joints and how they are arranged and connected define the kinds of movement or the motions we can execute. Movements are generated by muscles that produce forces. When muscles contract, they pull, but they cannot push. Sometimes we say you push with your muscle, but it's not true. We actually can only pull our muscles. So muscles are connected to bones through the tendons. Muscles and tendons span our joints. When muscles contract, they pull on the bones they are attached to, bringing the bones together. If we take a closer look at the joint that concerns us for our exoskeleton, the human elbow joint, we can identify certain characteristics that defines its functionality. So the elbow joint is a hinge joint. This means that we have one possible movement, often referred to as degree of freedom or DOF. So elbow joint has one degree of freedom, that is flexion and extension. When talking about human joint movements, the direction of movement is usually specified. Elbow flexion means that you move your elbow in such a way that your hand goes towards your shoulder, like presenting you in your impressive biceps. Elbow extension is a reverse movement. When you straighten your elbow joint, Accordingly, the muscles that generate elbow flexion are called elbow flexor muscles, and the muscles that extend the joint are called elbow extensor muscles. Examples of muscles that generate movement are the elbow joint. At the elbow joint are the biceps, which is a flexor, and the triceps, extensor. To move a joint, a muscle has to span that joint. For example, the biceps can also move the shoulder joint. However, this movement is not very important for us here for this project. So usually, full extension of the elbow from a straight arm, that we can flex the elbow until the lower arm touches our upper arm at about 150-degree flexion. So this tells us that the range of angle, the range of motion of the elbow would be 150 degrees. The range of motion is different for every joint. Also, there can be variation for the same joint between different people. Some people are more flexible and some people are more rigid. It is important to know that the range of motion of joints when designing an exoskeleton, for example, so the exoskeleton does not move beyond this neutral range of motions for safety concern. Otherwise, it can hurt the user when it is equipped with strong motors. For example, if we have a knee exoskeleton and we don't want our legs to be hyperextended, because that will cause a lot of trouble to our knee. But for example, this design of the exoskeleton, the range of motion exceeded the human body, that will cause a lot of trouble. So for our design for this elbow exoskeleton, please keep this in mind, that the range of motion would be from 0 degree to 150 degree. But of course, you can adjust it according to your joint. But please be safe. Don't cause any dangerous move. So when the muscles contract, they create a pulling force, F muscle, because of a lever arm R between muscle force and the joint center of rotation. The force results in a torque at the joint level that includes a joint rotation. So here we show this equation. If we want to move back, the muscle reflexes and a muscle on the other side of the joint, which is the triceps, contracts to pull the joint back. So for this equation, we can know the force and the torque. We can get this force and we can measure the R, which is the length of the arm, and then we can get the torque. And this torque, with this torque, we do know how to apply that to our servo motor. And when we are writing the code to control it, it might be very important. And that could be another safety measurement so that we don't hurt ourselves when doing this test. So for our project, we want you to design an exoskeleton to support the human. The exoskeleton is connected to the human, and the joint axis of the exoskeleton should be coincident, should be aligned with the human joint to ensure the kinematic compatibility. About the hardware and software. First of all, let's talk about the hardware. These parts will be provided: the servo motor, the microcontroller, the breadboard with cables, and this will be included in your Arduino kit box. You should be already looking at it. The force sensor, the load cell also. and the sensor amplifier, which will be in one kit, the force sensor and sensor amplifier, the IMUs, the Velcro straps, which can help you to fix the exoskeleton to your arm, the screws and nuts, which can help you to assemble the exoskeleton, the 3D printed parts, which will be designed either by you or provided by us. And you will also need to prepare something like the hex key set, the plier, or screwdriver if you need those. So let's look at this hardware we're going to provide. The servo motor. The actuator used in this kit is an electric servo motor with a gear and control electronics within the motor housing. The servo motor also contains an integrated potentiometer to measure the rotational angle, which is the position of the motor's shaft. In total, the servo motor has 4 wires, 2 inputs for the power supply, which are the red and the brown, or the black. It depends on the motor that you receive. And 1 input for control signal to the servo motor, which is the yellow one, the orange one. And there will also be another one, and 1 output for the angle signal from the integrated position sensor, which is the white one. It is common that servo motor have an integrated position sensor, but not all servo motor allow access to that angle signal. So sometimes there are only 3 wires connected to this servo motor. So the servo motor's integrated control system can already perform the basic very low level control. So for example, move the desired angle when command is sent on the control wire. When the command is sent through this control wire, and the desired angle is encoded using pulse width modulation, PWM. In PWM encoding, the desired angle of the motor is proportional to the width, which is the duration of an electric pulse that is sent to the servo motor on the control wire. This signal is sent at a regular time intervals to keep the motor at the desired angle. And the PWM, if you still remember that, we now can talk about it. It's on the Arduino board with the tilt in front of the digital pins. So we have 3, 5, 6, 9, 10, 11. Those are PWM pins. And this Arduino Uno, we've been learning a lot about it. So the main component of the exoskeleton electronics is the microcontroller. Microcontroller are essentially miniature computers that have all components in one board. Usually they have additional components and interfaces to directly connect to other devices. So for example, analog to digital converters and a variety of communication interfaces and buses. The microcontroller used for this exoskeleton would be an Arduino Uno, like shown here, like the one in your hand. Uh-oh. Sorry, my computer has something wrong with it. It doesn't work properly. Just wait a second, please. Can you guys see my screen now?
Yes.
Yeah, we see it.
Yeah, we see it.
Okay, great. So another hardware that we're gonna provide you is a breadboard. A breadboard is a rectangular plastic board with a bunch of tiny holes in it. These holes let you easily insert electronic component to a prototype, meaning to build and test an early version of an electronic circuit, like this one with, like the ones with battery, switch, resistor, LEDs. Actually, I think you are already pretty familiar with this because we had two labs that are using this one already. A force sensor, it will be like this one. We will provide a 10 kilogram force sensor, and here is the specifications of it. And HX711, which is a sensor amplifier. We are going to hook up the Arduino Uno and the force sensor together. And we're going to hook up the Arduino Uno, the HX711 amplifier, and this force sensor together. So the force sensor is basically a piece of metal that has special electric resistors called strain gauge glued on it. Strain gauges change their electric resistance when they are strained, or called being pulled, even by very small strains. When a force is applied to the force sensor, the metal deforms by very small amount, which are usually not visible to our naked eyes. So the strain gauge changes their length along with the metal, which causes a change in their electric resistance. So typically, several of these resistors are connected to a special electric circuit called a Wheatstone bridge that allows precise measurement of changes in electric resistance. The output voltage of this circuit changes when the resistor changes their volume. The voltage is the output signal of the force sensor and is proportional to the applied force. Because the output voltage is very small, it is connected to an amplifier chip, which is this HX711. This chip is then connected to the Arduino microcontroller that then read the amplified signal. Oh,
Yeah, I got a
by the way,
quick question.
Yes?
For this force sensor to be hooked onto the sensor amplifier, how is this wired? It looks like it's supposed to be soldered on. Are you guys going to solder it for us when sending it out, or?
No.
So
you're going to use this male-to-male jump wire to connect them.
Oh, jumper wires will work for this? Because it looks like it's supposed to be soldered.
Yeah, I know, but actually from this one, I don't know if you guys can see this one. The one I'm using, can you see this one? I just use this jump wire to it and apply this electric tape to tape it on.
Oh,
It
okay.
should work. Yeah.
All right, just wanted to make sure. Cool.
Yeah, no problem. Please feel free to raise any questions. Don't hesitate to ask me questions if there's anything you want to know.
So in regards to 3D printing, you guys said you guys can supply us with the parts as well. Can you guys give us the files sooner than whenever you guys intend to, so we can see if we want to adjust it in any way, shape, or form?
Well, actually, about that, we'll talk about that just about now. So the design of 3D printing, the robot design process would be design requirements. You know the design requirements, you have a design concept, and then you do a basic design. After we evaluate your basic design, you do a detailed design. Then the manufacturer approval, we got it 3D printed or manufactured, whatever that is, depends on the project. And the system integration test, and understand the unmet needs. For example, the this is just an example. The partial assistance for broader population, the limitation of conventional exoskeletons, that will be the full assistance primarily for paraplegic individuals with little to no remnant voluntary movement, and for the design of the soft exoskeleton or the wearable soft exoskeleton that will be suitable for people who need partial assistance, so on and so forth. So for this design, you have to know what are the requirement, what are the limitation. But for this one, maybe we don't have so much limitations because we want you to start a design of your own. But of course, you can check a lot of references to see what are the limitations, and you can expand from there. And then you have a concept illustration. So before you getting started to work on your design, you must have a very clear concept of your design and what you want to deliver at the end of this lesson. So maybe you don't have to do a presentation to us, but you have to know that for sure to yourself. Oh, sorry. Let me reopen this file. Can you guys see my screen now?
Yeah, we see it.
Yeah.
Okay. And then let's talk about the 3D printing. 3D printing or additive manufacturing is a construction of a three-dimensional object from a CAD model or a digital 3D model. The term 3D printing can refer to a variety of processes in which materials is deposited, jointed, and solidified under computer control to create a three-dimensional object with material being added together, such as liquid molecules or powdered grains being fused together, typically layer by layer. And this is a 3D printer we are using at our lab to print out the final project. Is the MakerBot, a replicator plus 3D printer. So to print the parts, you will need to export your files as STL files and arrange the layout inside their software called MakerBot Print. And for the question you just asked me about this 3D printed part, we are not going to provide you the CAD models because we want you guys to design your own CAD models. And you send your CAD models for us. We will validify your design to see if that is suitable for this project. Maybe sometimes it doesn't mean your design is not good enough, but just because, for example, the material we're using might not work well. How do I?
What material are you guys using?
I'm sorry?
Are you guys using ABS or PLA?
PLA.
Okay.
So we're gonna use PLA, and we know that PLA is not famous for its strength. So maybe your design is pretty good, but it just doesn't work well with PLA, or it's just too difficult to manufacture, or maybe it's just too delicate. Sometimes we will just decide, okay, we will give you the standard omni-axle parts, but you will not be provided the CAD model of the standard omni elbow axle before
Does the
you hand
software
out your
we're
design.
using matter? You
I'm sorry?
mentioned something. You mentioned last time about 2016. Does it have to be 2016 or?
It'll be better if you use 2016 or later, because
Yeah,
compatibility of the file.
I still wasn't able to get SolidWorks, so I'm gonna have a tough time trying to design it.
Okay, and
Just
we'll
saying.
talk about that just about now, the software part. So the SolidWorks is a solid modeling computer aid design, the CAD design, and a computer aid engineering computer program that runs primarily on Microsoft Windows. So for a lot of people, I know you're using the Mac OS computers. So I'm afraid you either have a boot camp or the parallel desktop or something installed in your computer. So hopefully you are very familiar with this picture down here, because if you were
Professor,
not,
you can use Fusion 360 for Mac to model with that. Fusion 360 is free.
yeah, I heard about that software. It's a pretty good one. I believe that's a free one, right?
Yeah, it's free.
Yeah, I think that's a free one. But personally, I don't have a lot of experience using that software, so I can't say anything about that software. The only thing I can say is that you are recommended to design your exoskeleton with SolidWorks, but you can also choose your preferred CAD software. For example, someone may like to use Inventors or etc. But like I said, we highly recommend you to design your exoskeleton with SolidWorks, because we have to think about a lot of things like the compatibility, because once you send us your design, we have to check and check if your design works, or if your design can be printed out, or if it's just too complicated to print it out. So we would recommend you to use SolidWorks. But also, if you just can't get SolidWorks, don't worry too much about that, because for the printing process, that will be using STL files. But also, if the Fusion 360 can also generate some files that are compatible with SolidWorks, that'll be fine too. So you don't need to worry too much about that.
So is there a way that you guys can get us a list of accessible software? I mean, you guys expect us to 3D print something. I would expect you guys to give us some sort of software that we can use and that's readily available, whether it be SolidWorks or anything else.
Okay, we will update that shortly after this lecture, and we will let you know. I think we will post that both in the Blackboard and in the Dropbox. And when we do, you will get an email notification.
Cool, thank you.
Hey,
yes.
Bowen, can you please go to the previous slide?
Yeah, sure.
Is the image in this? It's not
No,
it's not the arm, right? Because that looks too complicated.
It's not the arm. It will be a little bit too complicated for this arm exoskeleton. But if you are very welcome to design it to this level of complexity, but I would say it's a very short period of time to design something like this.
And I had a question regarding component-wise, right? So we also gotta consider where the placement of the component is gonna be on the arm when we're designing it in SolidWorks. So where is the most ideal location or place that we should consider to attach the Arduino board or whatever we're gonna be circuiting with it? Because we have to consider that for design purposes, right?
Yes. So I think in the previous lecture and labs, we sent out some demo videos and demo pictures. Those are just like one or two possible positions where to place all this Arduino board or sensors and stuff, you don't have to just do it according to our design, but for example, because you can extend the wires of the sensors, so you don't necessarily put the Arduino board on this exoskeleton. You can just use a wire.
Okay. And
Yeah.
one of the students is asking that if they made the design so efficient and cool and very good, is Hausu gonna recruit them in the lab?
That's a possibility. Actually, if you want to work for us, work at the lab, and if you're really good at that, we might consider that. Yes, there are possibility of that.
Okay.
But of course, you have to finish this project, and then maybe you can send us an email to Professor Su. And,
does that mean you have to be a student for in the college, or like if you graduate and the possibility is still there?
I would say always possible.
Yeah.
Yeah.
Okay.
I think Professor also talked about that.
I don't think he did that. But anyways, thank you.
No problem. So
I got another quick question. Sorry. So for the purpose of our final project, we're using a breadboard to hook everything up.
You don't have to use a breadboard to hook everything up, but the thing is, for Arduino Uno, there might not be sufficient pins.
Right, because I was
example,
thinking about using, I was trying to use a solder board, which is a lot smaller, and will do the same job as a breadboard.
Yeah, anything would be fine, but we wouldn't provide that. The thing is, we are providing the breadboard, so you can use whatever you want to use, make it as fancy as you want it to be. But the thing is, we are only providing the standard kit.
The bare minimum.
Yeah, the bare minimum.
And when it comes to 3D printing, if you're 3D printing on your own, do we still have to get it approved from you guys, or can we just do our own thing and just give you guys the final product at the end of the semester?
You still need to give us your CAD for validation, but the thing is, let me think. We will talk about that later.
Okay.
Thank you. So let's continue. We've already learned a lot about the Arduino IDE in our first lab and second one, and it is an open source software based on ongoing processing IDE development, and it's an integrated development environment officially launched by Arduino. By using Arduino IDE, you just write the program code in the IDE and upload it to the Arduino circuit board. The program will tell the Arduino circuit board what to do. And at this moment, I hopefully all of you has already installed this Arduino IDE either in your Windows laptop, your desktop, or your Mac. And here is how you hook it up: the Arduino board, the computer through the USB connection, and connect it with the your design of ARM exoskeleton. And let's review the code structure of Arduino. So the first part would be the variable definition. The second part would be the setup functions. They only run once at the very beginning of every boot. And then the loop functions, they run unlimited times until the, and this is the major part of the coding. You will do a lot of those coding here. The syntax. Each sentence of Arduino code consists of several elements: operator, variable names, consistent values, and you have to end it by semicolon. You must remember this because sometimes I forgot to write those two. A sentence started with double slash indicate a comment which will be ignored by the compiler. a block started with slash asterisk and ended with asterisk slash, also indicate a comment, but this one is a paragraph instead of a sentence. And here are the functions we're gonna constantly using: the setup, the loop, the pin mode, the digital write, digital read, analog write, analog read. And other than that, we will have a lot of other functions. For example, the flow. I highly recommend you to go to the Arduino website to read their library. You don't have to learn all of them, but it will be great if you learn the very common ones. So there are three major elements of a function: the name of the function, the parameters type, and the return data type. If nothing is returned, the return data type should be void. So here is a function example. And after you finish your Arduino coding, you will verify it, you upload it to your Arduino board, and then you open this serial monitor. You can monitor what is going on, and sometimes it can tell you a lot of information. For example, for this servo motor we are using, you can read the position of it through this serial monitor, and through that you can control your motor to make it move to the desired positions. And that will be today's lecture. Next lecture we will talk about the control of the sensors, the motors, and we will talk about a lot about the coding, actual coding. So if you have any questions, please let me know. And after, yes?
I have a it's not a question. I think for our first assignment, we were supposed to implement all of this, the serial monitor and the stuff you're going over right now.
I'm sorry, the internet wasn't so stable. Can you repeat your question?
I said for the first assignment, lab 1, we were supposed to we implemented all of what you're teaching us right now. We already have it implemented in our first lab.
Yeah, already did. So today's lecture, this part would be a review, and that because in the next lecture of this part, we will talk in depth about the coding for the control part. So today we just want you to have just a callback of all those memories if you haven't been using this for a while, and yes, just so you can refresh your memory of the Arduino IDE. So you should be already pretty familiar with this, with lab 1/2 and lab 2. Okay, now, so if you don't have any questions, let's have a 10 minutes break, and then we come back for lab 3. Is that okay?
I have a quick question about lab 1-2. So for the array code, it says that A15 are those numbers, and then is to generate the new array B13. By min, do you just mean that the numbers have to be organized from smallest to largest?
I'm sorry, let me look at those. So you're talking about task 3, write codes to achieve the following functions: loop and array.
Yes.
Give array A, which is 15, to generate a new code. I'm sorry, what was the question again?
By min, do you mean that like they have to be organized from smallest to largest?
No. So that would be the minimum of the three.
Oh, okay, got it.
Yeah. Any other questions? Okay, then please come back at 3:15 for lab 3.
Wait, do we come back onto this this Zoom link or?
Yeah, the same Zoom link.
Okay.